Okay. So I'd like to welcome you all to another edition of Quantum Fluids in Isolation. So today we have Professor David Ceperley. So once again, Ceperley is one of these people who doesn't really need an introduction, but I'm going to try to anyway. So Professor Ceperley got his bachelor's degree from University of Michigan in 1971 and his PhD from Cornell University in 1976. He then postdoced at the University of Paris and Rutgers University and was a staff scientist at Lawrence Berkeley and Lawrence Livermore National Labs. Starting in 1987 till present, he joined the Department of Physics at Urbana-Champaign, Illinois. And from 1987 to 2012, he has been staff scientist at the National Center for Supercomputing Applications. He's a recipient of many awards, including he's been a fellow of APS and a member of the American Academy of Arts and Sciences. He was elected to the U.S. Academy of Sciences and the UIUC Center for Advanced Studies. He's been the recipient of the Feenberg Medal in 1994, the Bernie J. Alder CSIM Prize in 2016, and the Xerox Faculty Award in 1996. And today he'll be talking about some new results in path integrals in superfluid helium-4. So please help me in welcoming, either by unmuting yourselves or by clapping virtually, Professor David Ceperley.
Okay, thank you. Actually, I'm going to talk about something a little bit different than you said. I think I sent you this abstract, but perhaps you didn't look at it. I'm going to talk about path integral theory of exchange in quantum crystals, not superfluids. And it's a bit of an old subject, but I thought it's maybe not as recognized as it could be. I think it's a very nice theory that I'm going to explain how you do numerics on it. Basically, it gives us an example of how we can go from a continuum Hamiltonian here, a non-relativistic Hamiltonian, into a spin Hamiltonian in a more or less rigorous and numerically accurate fashion. And so this would be useful if we could do this on strongly correlated materials. I'm not saying that we can, but this may be a goal. So I want to explain how we do this, and a little bit about the physics of that, and tell you, sketch how we do the path integral calculations and the applications to helium and to Wigner crystals. Okay, first of all, let me tell you about the physics of helium. I'm sure everyone is somewhat familiar with this. Shown above are the phase diagrams for the two isotopes of helium, helium-3 and helium-4, temperature, pressure, phase diagrams. And what makes helium interesting is the fact that it has a very simple interaction. A helium atom at low temperature and low pressures is basically an elementary particle because the electronic energy scales are so much higher and has a huge gap that you can assume that at a few degrees Kelvin, the helium atom is in its electronic ground state and never has any excitations. And the atom itself is not very polarizable, and it has a pair interaction like this. One of the things is shown is the Lennard-Jones interaction. The other one is a more accurate interaction. They don't differ very much. The main feature is that you have this hard sphere interaction at 2.5 angstroms, and then you have a weak attraction. Because the attraction is so weak compared to the 0-point Debye frequency, you don't have a liquid. A liquid is the ground state, and that's superfluid helium for helium-4 bosons, and for helium-3, which is a spin 1/2, you have the superfluid state also, but at a much lower temperatures, at a millikelvin temperature. This is not what I'm going to talk about. I'm going to talk about up here in this corner of the solid helium. what are the magnetic properties of solid helium. And you also have a transition at millikelvin temperatures, as shown. Okay, first of all, a little bit about solid helium. Normal classical crystals melt according to Lindemann's rule, namely when you have the RMS vibration is something like 14% of the nearest neighbor spacing. Helium, however, is very quantum mechanical at these pressures, and it melts only when the RMS vibrations motion is something like 30% of the nearest neighbor separation. At low temperatures, you have a huge separation of energy scales in the problem. So you have electronic energies, as I said, are more like 1,000,000 Kelvin. The Debye energy is something like 10 Kelvin. And the direct magnetic energy, that is, if you have the nucleus has a spin, the spin-spin interaction energy is like 10 to the minus 7 Kelvin. And what we'll find is the exchange energy, which is caused by atoms exchanging places, is more like 10 to the minus 4 Kelvin. And it's that energy which determines the magnetic properties of helium-3. Now, this is a hexagonal picture for two-dimensional helium, but in 3 dimensions, it forms a BCC lattice, not shown here. And that's a bipartite lattice. And so I think the physicist's first guess as to the magnetic order would be antiferromagnetic, because BCC is a bipartite lattice. However, when they did the experiments, they discovered something else. This was experiments in the 1970s. This, as you see, is a low temperature. So this is a millikelvin temperature. There was a phase transition here. This is the paramagnetic phase. And at low magnetic fields into a so-called low field phase, which was eventually discovered to be the so-called U2D2 phase. It's a broken symmetry phase where you have 2 planes of upspin, 2 planes of downspin, 2 planes of upspin. So you have a bigger unit cell, and it's, you have broken symmetry. The XYZ, 90 degrees rotation symmetry is broken, so it orders in one particular direction and not the other. You also have another phase at higher magnetic fields that I won't really get into. The question is, though, how can you go from this simple BCC crystal into this kind of broken symmetry phase? What causes it? Now, the theoretical picture of what causes the magnetic interaction is due to David Thouless. You probably know him from his work. He got the Nobel Prize a few years ago on topological phases, on quantum Hall effect and other things. But in 1965, he wrote this pair of papers about exactly this problem. This is before the experimental situation had been explored, before they could do these things at millikelvin temperature. And he gave us a very simple picture of ring exchanges in solid helium. Now, something that even the experienced people in the audience probably didn't know is he also wrote a companion paper on quantum Monte Carlo in the same volume in 1965. It was a pretty crude quantum Monte Carlo, I have to say. He did 2 hard spheres in a box and tried to find out what the exchange frequency is. So it's really this first paper, which was a theoretical paper, which had a big impact. I should say, this work, he built on some earlier work of Conyers Herring and Phil Anderson, some other people, that was particularly oriented at magnetism, that is exchange of electrons. And so he was really thinking more about the exchange of helium and how that changes the problem. Now, this is what I call the Thouless theory, of the magnetic ordering in helium. And basically, at low temperature, there are very few defects. That's important. You don't have vacancies or interstitials or any kind of impurities. Phonons are pretty much frozen out also at millikelvin temperatures. So thinking about the many-body wave function, well, the wave function, if you have n atoms, if you don't have any vacancies, you have n factorial peaks of a peak being suppose you number the lattice sites from 1 to n, and you number the helium-3 atoms from 1 to n, you can arrange the helium atoms onto the lattice sites in n factorial ways. And they're very sharply localized around this arrangement, and you have very narrow, what he called ducts, of way the system can travel from one arrangement to another arrangement. And essentially there has to be a tunneling process that I'll show you in a few minutes. And so the idea is basically you expand the many-body wave function, which must have anti-symmetry, in terms of localized wave functions where you assign atoms to arrangements. He speculated then the dominant tunneling rates are few body cycles, as I drew here. For example, right here is a pair exchange of atoms. Here's a 3-body exchange. Here's a 4-body, 5-body, 6-body exchange. Those are ring exchanges. And so the idea is that basically this system goes from an arrangement like 1, 2, 3, and it rotates into a different arrangement. And there's a rate for that happening. And we can view that as a permutation operator. And he says that the actual Hamiltonian that guarantees the spin arrangement is this uninteresting phonon part, which is pretty much frozen out at low temperatures. Plus there's this exchange part, and we expand in terms of permutations. And in particular, these, all permutations can be written as cycles. And so we're interested in permutations with one cycle. And that would be like an exchange of 2 atoms or 3 atoms or 4 atoms. And what he was easy to show is that if we take these J's as the exchange frequency, then there's a sign that comes up which is even or odd, depending on whether you have an even or odd number of atoms exchanging. So even exchanges turn out to be antiferromagnetic, and odd exchanges are antiferromagnetic. And I also showed that if you just have 2- and 3-body exchanges for spin 1/2 particles, you end up with a Heisenberg model. Whereas you have more complicated Hamiltonians if you have higher body exchanges. Now I'm going to explain this again, although I'm sure you all know this is really elementary quantum mechanics. If you consider one particle in a double well, then you can, if a symmetric double well, you can write it, there's a splitting between wave functions that are even or odd under exchange with respect to the center of the well. And we can expand in terms of left states and right states. We can expand in terms of symmetric or anti-symmetric states. And what you find is that if you started out on a state localized on the left, it will oscillate left to right with a frequency given by the splitting between these 2 levels. Now, if we now generalize to 2 spin 1/2 particles in a double well, like this, you have to couple the spin with this localization left to right. And so the ground state is a symmetric with respect to the center of the well, the origin, and it's anti-symmetric with respect to the spin. That's the singlet. And the first excited state is the triplet state, and it's anti-symmetric, like in the previous. And again, J2 is the frequency which the spin now will oscillate from left to right. We can replace for spin 1/2 by two product of poly matrices, and we can write that as a spin Hamiltonian. Or we can write this in terms of the permutation operator, which is more general because this notation, which is what will follow in the rest of the talk, doesn't have to be changed when we go up to 4, 5, 6 body exchanges. Now, let's put in the hard sphere interaction between helium atoms, and we consider this problem, which is similar to the problem that Thouless did his Monte Carlo on, although he had a rectangle instead of two. Let's take two spheres, hard spheres, and a single particle is confined to the interior of these two spheres, and the spheres touch. So there's open what he called a duct between these two wells, right? And what's shown is the imaginary time path of a particle in this potential well, and it spends a very long time bouncing around inside of one sphere, and eventually finds this hole to the other side and goes to the other side. And in imaginary time, we call this an instanton. Here's a picture, a space-time picture of this actual path. This is just a XY plot, and this is X and imaginary time. And you see it spends a long time in one well, and then it crosses to the other well and vice versa. This is actually the model to think about on helium. It's different than electrons would be because of this hard sphere interaction. So in there's a group of French physicists, Michel Roget and Jean Delrieu, who talked about the metro effect. And so here's a picture of the New York subway. And the idea is, think about if somebody wants to get off at a stop on the metro and it's really, really crowded, a single person can't do it by him or herself, right? It requires a cooperation between all the people in the subway. And basically, in order for, say, a person back here to get off, maybe these people have to get off to make a passageway, or else there has to be a rotation of the people. And it's this effect which causes a long ring exchanges to be favorable. That would be true in a metro too. If it wasn't crowded, then people wouldn't bother to move out of the way when somebody wanted to get off. But if it's crowded, there has to be a cooperative motion in order for people to get off. And it's this effect which makes solid helium-3 so interesting, because of the long ring exchanges are as favorable as the short exchanges. And it's the large cancellation. Remember when I showed you this Hamiltonian, the sign depends on the number of members that are exchanging. And so if the probability of 3-body exchanges and 4-body exchanges is about the same, they'll pretty much cancel out. And this U2D2 phase in solid helium is the thing that minimizes the energy in the Hamiltonian, because it's able to have ferromagnetic arrangements of nearest neighbor, but antiferromagnetic arrangements of ones that are a little further apart. That's the optimal way of putting spins on the lattice. But the thing that caused a lot of resistance back in the mid-'80s was that it seemed to require fine-tuning the J's, that is the J2, J3, and J4 would have to somehow be close to equal to each other in order to get the right phase diagram corresponding to experiment. And so there's really resistance to this so-called multiple exchange model, because you had to explain why these exchange frequencies were close together and not, that because they're a tunneling process, which you usually think is exponentially activated. Now, I'm going to now switch to talk about how we did these calculations and give you some results. I guess our host just didn't say that you could ask questions. I could stop.
Yes, so if you have any questions, just please ask.
David, a simple one. Can you go to the previous slide? And I see there a remark in green that is rather surprising, right? So it's order out of disorder. Did you get solidification? What's the story there?
Well, you can basically ignore the attraction between the atoms when you're discussing liquid or solid helium. You won't get the pressure right because the attraction adds to the pressure. But basically, are you asking why it forms a solid? I mean, it's basically in a solid phase, well, classically we would call it entropy. There's more, it gives the atoms more space if they're arranged neatly in a solid, and they need the space to minimize their 0-point energy.
Right, so quantum order out of disorder, right?
That's right.
Yeah.
Well, it's not.
I didn't know that. Interesting.
It's not only quantum. The same is true classically. If you take hard spheres and you compress them, they will form a crystal eventually, because in that case, they're maximizing their entropy in the crystal, which is a little counterintuitive, but it's true.
Yeah. That story I know. But I didn't know it's true in helium.
Yes. I mean, in order to get the pressure correctly, you have to put in the attraction, but that's pretty much just a constant. Okay. Okay, so I'm going to describe now how we do the calculation, and the key ingredients come about by Feynman's imaginary time pass, which he explains superfluid helium, and this famous metropolis algorithm, which we use all the time, of course, in statistical physics. And the first ingredient, well, I think I'll skip over here, the density matrix. This is explaining a little bit about path intervals, but basically, this is an exact mapping from quantum statistical mechanics into classical paths. So this is the partition function of a quantum system, and you can express it as an integral over paths. I'll show you in a picture. Times what we call the action, S. The action consists of two terms, the kinetic part and a potential part. And here's a picture which is maybe easier to understand it. This is of 6 helium atoms in a box, and basically the quantum system is mapped into these ring polymers, these 6 ring polymers here, and these are just periodic replications. And so the quantum mechanics, the kinetic part is the fact that you have this spring here, which you have all these other points on the path besides this point. Classically, you would just have the black dots. But quantum mechanically, you have the whole path. And basically, in the Monte Carlo procedure, you have to move the atoms and you have to move the path. And there's an explicit probability for the path, which is what I've shown right here. This is the probability. You have to keep the atoms apart with the potential. And then this is a spring term, which keeps the points on the path close together to each other. The lower the temperature, the longer the string or the elastic band. And so eventually when you have solid helium, it kind of fills up the whole lattice site. And that represents the wave packet. And again, this is an exact mapping from quantum statistical mechanics into classical mechanics. Now, we're going to describe then how we do the path integral calculation of the exchanges in the crystal. I call Z here a perfect crystal arrangement. That is assigning and then numbering the atoms, the helium atoms, and assigning them to lattice sites. PZ would be another arrangement. And we're concerned with just say 2 or 3 body exchanges. And so P is like exchanging 2 atoms from one latticite to another. Okay, what we do is we calculate this ratio here, where Q is the partition function to go from a latticite Z to a permuted latticite, P of Z, like a ring exchange, like a 2-body exchange, for example. And this is the path integral action to going from Z to PZ. So this is like a partition. Normally, partition functions or free energies are difficult to calculate in Monte Carlo, but we're taking this ratio of them. So it's a question of how much free energy does it cost to insert a permutation into the lattice, that is, to make them do a pair exchange, okay? And what I show on the next view graph is that this is basically a tanh function, and the argument involves this exchange frequency that we want to have. This is actually what the exchange path looks like. Well, this is, the top one is what it looks like. This is imaginary time here. That is, we give it an amount of imaginary time beta to go from one latticite here to another latticite here. We force it to do exchange, but it has a whole different, it can do the exchange at any time at once. That's why there's a whole bunch of different exchanges here. Here, what we did was we collapsed them onto one curve by making sure they all crossed at the same instant of time. And you see that all these different exchanges are basically all the same, except you have this one variable, which is when they actually crossed. And that's why it's linear here. The free energy ratio is linear in imaginary time. It grows. The longer time you have, the bigger it is. It's classical entropy, basically. And beta 0 in this formula here is basically the width, this width of an imaginary time of how long it takes to cross the barrier. Okay. So anyway, I don't think I'll go through this algebra, but this shows you why that is true. That basically, if we expand in terms of an even function and an odd function, and there's an exchange frequency, basically these using the fact that the many-body wave function is either symmetric or anti-symmetric with respect to exchanging those 2 particles, then you know what comes in as the excitation energy, and you can write this as a tanh. And here's some calculations with different values of imaginary time, and you see that it does follow a linear slope. And the slope is the exchange frequency. Or you could say in terms of this picture, it's basically the probability that this ratio here is the probability that a system would naturally want to exchange in imaginary time. It's the rate of exchange. So there's a close connection between the rate of exchange in imaginary time or real time. They're basically governed by the same J. I think maybe this is more of the details of how we do it. Basically, we do 2 calculations, which we call A run and B run. A run is consider all paths that where particles are sitting on lattice and they're returned at the same site. B runs are ones where you force them to make an exchange, and you continually try to convert A's into B's and B's into A's, and you figure out the probability. Charlie Bennett, one that invented this for classical systems, and we just borrowed this. So that's the Monte Carlo trick. And so basically, and when we try to convert from A to B, you know, this is say an A path because it goes from this lattice site back to the same lattice site. This is for a brown particle and a green particle. And these are spectator particles here. And we actually just do an exchange we make an exchange by exchanging the midpoints and then the midpoints of the midpoints until we have the whole path worked out. And then we calculate the probability that we did that, and that gives us everything we know to calculate this ratio of partition functions. And the advantage of this, well, these are kind of technical points, but this exchange frequency is computed as a ratio of rates, not as a difference between small numbers. Okay, so you have a direct way of calculating J's by essentially how much work, classically, how much work do you put in order to make two atoms exchange. You don't wait for them to happen simultaneously. If you do good sampling, you have what's called a zero variance principle. So the better the sampling is, the lower the variance of the Monte Carlo is. It's kind of an order in method. That is, if you have 1,000 atoms in your system, your effort is concentrated on the two atoms that are exchanging. So we can do long exchanges. So that is actually the method. Are there any questions about that?
So in general, could this be used to get tunneling matrix elements? Let's say in some, let's say you absorbed helium atoms onto a surface, graphite or something like that, and you're interested in an effective Hubbard model. You could use this to get T?
Oh yeah, definitely. That's kind of what the subtext of my talk is, yes. Okay. We could use it more generally. I should say there are some assumptions in this theory that you would have to think about whether they affect the results. But, and I'll talk about one of them in a minute, but yes, and I mean, I'm applying it to a situation that's completely symmetrical, namely, you do this pair exchange, you end up essentially back in the same place, just a different arrangement of atoms. But what you talked about, you might end up, it might not be a symmetrical barrier, but right. It can be generalized to that case.
Okay, that's interesting. Thanks.
I have another question, Dave. Again, a stupid one. Could you simulate it full blow, that you just load up your quantum Monte Carlo machine with your helium atoms, and then it wants to solidify, and you could read off the spin configurations, or would that die on terminal signs or something? How does that act out?
I didn't quite understand all of your question.
Oh, very simple, right? So you could just load up your machine with zillions of helium atoms, let the quantum Monte Carlo run forever, go to very low temperatures, find a solid with the right spin order. Would that be manageable, or would that die on fermion sign problems whatsoever?
Yes, it would.
It would die on fermion signs, right?
Well, actually, the way we're doing this calculation, we're calculating this Hamiltonian, the spin Hamiltonian, the coefficients in there. The next step is to take that spin Hamiltonian and then do some method to calculate its properties. And what we did was exact diagonalization, because it could do that on a Heisenberg model up to, say, 54 sites or something, which seemed to be big enough.
It's like a frustrated Heisenberg system where you have, again, fermion signs.
Right. Well, of course, it wouldn't have to be frustrated, but our cases, they are frustrated.
Typically are, right? It's hard to avoid it,
So now, even when you get to that part, yes, we could take atoms and we could end up with the J's naturally. We preferred to put in more physics and make it a lot easier when we did this 30 years ago. But you could now actually, you wouldn't have to target the ring exchanges. You can now do it so they would come out, and it would tell you whether that picture is relevant or not. I think you could do that if you didn't know that already. But the part of going from the spin Hamiltonian to the ground state properties, well, that's a harder problem, but it's possible that people could do that. here shows some results. And so basically, I'm going to just show that these are the results over here in this column here. And these are in microkelvin. And basically, this column here, so these are the number, these are two particle exchanges. And they all, on a lattice, they all have different names to them. And I won't tell you what they all are, but they're different types of like planar, folded, and so forth. But the ones that you might easily think of are pair exchange, this 3-body exchange, and this 4-body planar exchange, right? And these are the numbers that were gotten from backing out of experiment. So we want to talk a little bit about that. And this is what we calculated. And so they're not exactly the same, but if you look over here, you see that it's true that these 3 large ones are the 3 large ones we calculated. Okay. Now, if only 2 and 3 atoms exchange, you have a Heisenberg model, but you can't neglect the other exchanges. I'll show you that in a minute. There's 2 things that we can calculate, or there's 3 things we can calculate without doing many-body physics, namely the magnetic susceptibility. It's called the Curie-Weiss temperature. Oops, sorry about that. Theta, and that's just a combination of the J's. The heat capacity, I should say, also the the magnetic field that's required to make it totally spin polarized. You can also calculate directly from the J's. You cannot solve this Hamiltonian here except with exact diagonalization. And you could do it with exact diagonalization for like 54 spins or so. And people have done that. Here's an interesting plot, I think. This shows the Curie-Weiss temperature in millikelvin and versus how many spins in the ring exchange you include. For example, if you go up to 4 spins, you get this value. If you go, including all 5 spins, you go up to this value. And you see it converges quite slowly. And this is experiment right here, this shaded green box. And this is the magnetic field at which it becomes ferromagnetic or spin polarized. And that's actually up here out of my graph, the experiment. And this also shows this, it alternates, of course, because of this -1 to the p, that even and odd spins are ferromagnetic or antiferromagnetic. But the lesson is, even this simple model of helium, it can lead to these many-body collective effects. And this is why we don't agree with the J's that were backed out of experiment, because they only assumed that there were 3 frequencies that came in, and actually there were a lot more. But if we compare to experiment, here's the comparison versus density. This is the Curie-Weiss temperature, and we pretty much exactly agree. The Monte Carlo is a solid line, and the experiments are these points. The magnetic field differs a little bit, the solid line versus the experiment, but the experiment has a lot of difficulty, right? And they can't actually go to the full magnetic field. So, at those temperatures, it's kind of difficult. So, probably we don't want to agree perfectly with experiment. So anyway, overall, I think we succeeded in using Monte Carlo to predict the spin Hamiltonian, and it shows that that collective effects can actually be quite important in these magnetic models. Oops. Here's one paradox, which I think you touched on when you asked me. There's actually a kind of a breakdown in the Thouless theory when you get too close to melting. And if we look at energy versus density, this is just something I drew, of course. And this is the energy of the solid at high density. And here is the energy of a bosonic liquid. This is if we ignore the spin 1/2, the same mass, but with Bose statistics like helium-4. And this is the Fermi energy, okay? And it has to be higher because you pay an energy to make the Fermi liquid sort of on the order of the Fermi wave vector squared over m, okay? And so it's higher. So there's a region around melting where if you ignore Fermi statistics, the solid is actually unstable and would melt. So even though the exchange energies in the solid phase are really small, they're millikelvin, they serve to stabilize the crystal versus the liquid. And so indeed, when we get close to melting, we find it great difficulty in converging our expansion. And one speculation might be that these long ring exchanges are the things that are actually leading to melting. Okay, we had to have special techniques that in order to stabilize the crystal, no melting. Now, a second point that I want to raise, the question is why these long exchanges are have all about the same probability as the small ones. I mean, they do converge away from melting so that, you don't have infinitely long exchanges. But here's the picture that I've always been drawn to. It's what I call vacancy interstitial fluctuation model. Well, basically, if you take an atom, and as I said, that the 0-point motion of the atoms is really quite large. And so maybe by chance it fluctuates and creates an interstitial over here and a vacancy over here. Well, the vacancy has a very low mass and it will rapidly start to diffuse around the lattice. And then it will eventually come over here and combine with the interstitial and annihilate each other, right? And so that's the model, basically. And so because the interstitial has such a low mass, it can go pretty far and it can scramble all the spins in a whole region while it's looking for its mate, its interstitial over here. And it's attracted to that mate because these, if it weren't, then you would have vacancies in the crystal. That's a bound state. And this would explain why all the J's have a similar prefactor or a similar rate and similar density dependence. And it would also sort of explain why you can change the potential of interaction. You get pretty much the same Hamiltonian. I didn't show any data of that, but we've compared like a Wigner crystal to helium near melting, and they're rather similar spin Hamiltonians. But the problem I've always had is how to prove that this model is actually correct. I mean, there are a lot of suggestions it is, but it's hard to actually show that it's a correct model, well, at least of why you have long spin exchanges. Now, I'm going to switch gears here. I see I have 10 minutes at least. We've been recently doing calculations on the 2D Wigner crystal. I think probably everybody knows what a homogeneous electron gas is. Basically, we're going to work, and the data I'm going to present is in 2 dimensions. So you have a Coulomb interaction between the particles, a repulsive 1/r interaction. And you have a background, so you get charge neutrality, and it converges thermodynamically. And you have the kinetic operator. You have temperature as a parameter, and you have density as a parameter, which you parameterize as RS. And RS, it's thought that the 2D Wigner crystal melts at around RS of 30. And there's a kind of a plasma phase. Now, you've heard about Wigner crystals in the laboratory. Those are way over here in this region up here. Like, well, there's a lot of applications. Electrons on the surface of helium is pretty classical, but electrons at semiconductor interfaces are quantum mechanical. Maybe ITC superconductors have some of this physics, probably not. Or graphene, people have been talking about that. People thought about using them for qubits. Unfortunately, these systems all are not perfectly homogeneous, so we don't have really good experimental data on the quantum Wigner crystal. So this is more of a theoretical exercise. Now, a few years ago, we did some calculation of the Boltzmann phase diagram, and here's kind of a picture of the Boltzmann one. And what's characteristic there is a hexatic phase because it's two-dimensional. And here's the Wigner crystal phase. And we found some unusual things down in here in this reintral liquid, which is little bubble phases down here. And there's actually, if you convert this into a bosons, you have a superfluid transition also. Now, what we've done recently is look at the spin 1/2 Wigner crystal, and we've traced out the melting line here, which is, this part is pretty classical, so that's the same as before. The red X's are the crystal phase, and the blue dots are the Fermi liquid. And it's kind of hard for us to go down here, but you can see comparison with what I just showed you, that the fermion crystal is more stable than the Boltzmann crystal. Now, in terms of the ring exchanges, we found again, we did again these 2, 3, 4, 5, up to 6 particle exchanges, and we found the frequency of them. This is now in terms of Rydbergs, and this is the region where we feel like maybe the Thouless model is breaking down because of the melting of the Wigner crystal. Now, one of the differences with Coulomb interaction from a hard sphere interaction is they can, the paths can get a lot closer together. I mean, the GFRs or the pair correlations look similar, but they're not exactly the same. And this, causes some important differences in which exchanges are important. And so we came up with this phase diagram. And here again is the Curie-Weiss temperature, which for a two-dimensional hexagonal lattice has this form in terms of the J2, J3, J4, so forth. And based on exact diagonalization, we think it might be a candidate for a spin liquid. And this would be the critical temperature. This is based on a diagram which my collaborator, Bernard Bernoux in Paris, worked out in terms of, there's a lot of parameters, okay, because you have J4 and J6, that is 4 and 6 body exchange. And you also have 2 body exchange, and well, you have 2 and 3 body exchange can be put together because they act together. So that it becomes an effective 2 body exchange. And so this J4 and J5, and then you also have J6 on here. And so this is something like a spin liquid down here. And we think that the 2D Wigner crystal follows a trajectory like this in Hamiltonian space, which is pretty much in the spin liquid regime. And interestingly enough, if you do 2-dimensional helium on a substrate, you end up with pretty much the same place in phase space. So that's what my remark earlier was, that there seems to be an almost universal spin Hamiltonian if you have 2-dimensional spin 1/2 fermions. But whether this is exactly a spin liquid or not may require more extensive calculations, which we've been working on. So I think, well, I just want to say another application we did about 10 years ago was in terms of supersolids. It's really the same code could be used for that too. And you probably heard all about this in 2004 if you were doing research back then. This is a picture of New Science and made in New York Times and everything. Well, what is a supersolid? Well, a supersolid is both a crystal and a superfluid. There's different types of supersolids, and this is the original definition, that is something that broke translational symmetry. There wasn't an underlying lattice, it formed its own lattice. And it's a superfluid, meaning that if it's oscillated, it has a non-classical response. It could have boson sign condensation also. And the question is whether you could get both things at the same time. And Penrose and Onsager thought that that was not possible. But Andreev, a little later on, said, well, if you have ground state vacancies, then it certainly will happen. Now, how do we see superfluidity in our calculations? Well, we introduced this measure called the winding number, which is basically if you take periodic boundary conditions, you have to have paths that wind across the boundaries. That is, if this is a torus, it'd have to go around a torus. In other words, it means you have to have exchanges which are long range, go a macroscopic length. And this is sort of a topological property of the ring polymers that they have to have. And so basically we can say in terms, now we're talking about solid helium, that we can assign a winding number to a ring exchange if we go across periodic boundary conditions. If it crosses the periodic boundary conditions, it has a winding number. So we can formally say the superfluid density is given by, the mean squared winding number times the exchange frequency, and then there's a prefactor here. And this has to be greater than 0 in the limit that your cell becomes macroscopically large. Localized exchange, like 2 or 3 or 4 body exchanges, don't transport any mass, so they're not related to superfluidity. And so we did actually calculate, this is an example of a winding path where you take a crystal like this and you just slide a row over. And here's actually a calculation of the exchange frequency versus the length of the path. And you see it exponentially goes to 0 because it's the logarithm. It's quite a simple exponential curve. So no, it can't, these type of paths can't lead to superfluidity. But you might say, well, what about all the other winding paths? Like once there's an exponential number of them, for example, they go up and down. And, what about, a path like this, there's a lot of those. Could this compensate for the exponential drop? And so we looked at for those paths. We calculated a lot of them. And we calculated a bunch of exchange frequencies. Well, I didn't show you the results, but basically we showed that you can make a model like this where and this is the action or the probability of a path, and you have a term which is proportional to the length of the path, and you have a term which is proportional to how many kinks you put into the path, right? And okay, so you have alpha and alpha prime are 2 parameters that we calculated for helium-4, and we were able to show that this is the superfluid or supersolid phase over here. This is the normal phase, and helium is here, is definitely in the normal phase. And I should say, about 5 years ago, the experimentalists basically figured out why they were seeing supersolid signatures. It had to do with acoustic responses in their apparatus and not with fundamental physics. there's still some unusual phenomena, but they don't have to do really with pure, perfect crystals of solid helium. They have more to do with dislocations and disclinations and things like that in solid helium. Okay, so I'll stop here with my summary. I hope I give you some idea of what you can do with these imaginary time path integrals. And they not only can be used to calculate, bosonic systems and superfluid helium, but the same types of technology can be used to calculate this microscopic Hamiltonian. And of course, is this Thouless picture for helium-3, where it's really been extensively tested, seems to be correct. That is, the magnetic properties are due to the rare ring exchanges of hard spheres. And we make them not hard, but with a realistic potential, and we get agreement as good as pretty good agreement with the experiment, as good as the experiment is. But I guess what I want to close with is, well, in condensed matter, theoretical condensed matter physics, people dealing with correlated materials, and you have all these spin Hamiltonians like the Hubbard model and the two-band Hubbard model, three-band Hubbard model. And people do come up with ways based on density functional theory of calculating the exchange frequencies. But those methods wouldn't work for solid helium because it's, it's much more of a hard sphere interaction. But it'd be interesting to know if somehow these methods could be extended to electronic systems. I bet that when we actually calculate those parameters, you're not just going to get a Hubbard model or two-band Hubbard model. It's going to be similar to the helium-3 case, where you have a fairly complicated Hamiltonian to deal with if you're going to get quantitative agreement with the experiment. Okay, so I'll stop there.
Okay. Yes. So now we begin questions. Professor Silvera, I see your hands up, so maybe you can unmute first. So I think you're muted. Okay, now you're unmuted.
So David, hi David.
Hi.
I didn't understand one thing. In the magnetic helium-3, what causes disorder first? Is it the thermal fluctuations between the spins, or is it the melting of the solid?
What causes melting? Is that your question? Or what causes the
What
spin?
causes spin disorder?
Oh, well, it's it's temperature. The exchange frequencies are a fraction of a millikelvin. So you don't get the spin ordering until you get down to millikelvin temperature. And it's just simply the entropy, the spin entropy, which causes it at temperatures above 1 millikelvin. Is the energies of the J's are in the order or less than a millikelvin. And, so you don't get the spin ordering till you get temperatures below that.
So it's the thermal fluctuations.
There's thermal fluctuations in the spin channel, though.
Yeah, I had one more question. Is it possible to get magnetic order in the liquid if you could go to low enough temperature with this exchange?
Well, one thing, the model itself, the Thouless model, does not apply to the liquid because you don't have the equivalent of lattice sites. And so, they're moving around. You don't have that. But the other answer is that, of course, a superfluid helium-3 is a form of magnetic ordering. It's just different.
Okay.
It chose to go into that. Yes.
Okay, thank you.
Okay, Professor Zanin.
Yeah, David, I wonder, you are aware that in insulated cuprates there is evidence for these ring exchange, 4-point ring exchanges?
Is there any evidence?
Yeah. It sort of modifies the high end of the magnetic spectrum. I think it was Ceperley also who nailed it.
Yes, I'm not familiar with recent work. I know back there were some. What's that?
It's old data, I guess. 50 years ago or something.
Yeah. I know that there were people working on that. I haven't really followed up on it.
There's a lot of questions. I really have a question, and the question is that at least I may be a bit brainwashed, but when you're talking about, you know, getting closer to the melting of either classical solids or bosonic solids, right? That you really have to worry about dislocation, anti-dislocation loops, blah blah. Right? The dislocations are usually perhaps way more important in the melting or the approach to the melting transition than interstitials are, right? It's also intervening, I guess, with the supersolid theme that you melt by dislocations and not by single interstitial excitation whatsoever.
Yeah, I mean, that's possible.
I know how to think about it, this context. For Fermis, I guess it's a bit of a hell, but when you would consider these kind of virtual processes, what kind of exchange phenomena would they give rise to?
Well, I think those energies are quite a bit larger. It's a good question, actually. And so I pulled up our Boltzmann phase diagram. And of course, you know, you have this thing right there, and that's definitely the physics. I think the answer is we actually have a tricritical point here. And I think that really separates the region where those things are important from when they're not. I think down at this low temperature region, they're not important in the strictly equilibrium phase. Now, in the helium experiments with the supersolid, a lot of the problem is that you're not really doing equilibrium physics. That is, there's not a lot of non-equilibrium things in there because you have, when you grow the crystals, you have built in a lot of dislocations and other types of garbage in the crystal. And there's no, you just can't make, it's just such a soft crystal. They say it's like toothpaste. And you just can't avoid that if you're going to do things like change the pressure or change the density or the temperature.
It's all about core energies, right? And the core energies of dislocations in these helium van der Waals crystals have been computed. They are known. I mean, it's a hairy quantitative business, right? That the dislocations or interstitials are cheaper. I mean, the dogma is in normal solid dislocations always win out from interstitials. For good, simple energetic reasons.
There have been some calculations in helium, and there's some measurements in helium. But no, I think the dislocations would have quite a bit larger energies, I think, but they get frozen in.
But why do you think that?
Sorry?
Why do you think that? It's not the rule. The rule is that interstitial substitutionals are way more expensive than dislocations, and therefore iron is riddled with dislocation because it's plasticish. And the density of interstitial substitutional is very, very low.
I'm sorry. Are you talking about in 2 dimensions or 3 dimensions?
It doesn't matter. It doesn't matter. True in all dimensions. The melting is a bit of a hairy issue, right? Because beyond 2 dimensions, right, you run into sort of hard first order transitions. Although you can still argue that dense classical liquids, as old Frankel view, are basically solids. There's lots of dislocations.
Yeah. I mean, I thought the trouble with the dislocations is, you know, you're moving a whole line of atoms, whereas an interstitial is a
no, it's a core. There's just a dislocation core, and you have long-range strains. But when you make a pair of them, dislocation and dislocation pair, these strains are partly neutralized.
Yeah. Actually, I don't know really.
You don't know, right? You have a look at it, and I wonder how dislocation loops can actually do ring exchanges.
Yeah.
Clue, yeah. Actually interesting.
Yeah, there would be. It actually, we did a little bit of that with the supersolid, but it's pretty tricky business because it was hard to relate to experiment because they don't really know what they have. And once you start putting in, you make them, you have a lot of dislocations and things you're not really sure what's in the sample anymore. And because of this long range interaction of those things, you needed to take big systems.
Yeah, it's hard work, right? To compute.
Yeah.
Any other questions?
Hey, Professor. Great talk. I have a little bit of a technical question. I'm curious. You talked about how we want to prune these undesired paths. It wasn't the slide when you were talking about the zero variance.
Yeah.
And I'm just curious, how do you go about pruning these undesired paths? Let's say you start your simulation. How do you know which paths would you want to throw away?
Well, let's see. If
I think it was the slide had a column of text that said, like, this is a bunch of technical stuff, and then a block of red.
I think I just went up past it.
Yeah, that one.
Okay. It's a bit, well, okay, it's not too long of an answer. You're trying to estimate the probability of making a transition from the A path to the B path, or vice versa. And what you do is you generate a whole tree of these things, sort of in parallel. And it turns out if the probability is sufficiently small, you can eliminate it. That it won't have no effect on the answer. And basically, this gives you a way to prune it, is once the probability, you set a limit of say 10 to the minus 6. If it's smaller than 10 to the minus 6 probability, it's not going to affect the answer. And then that becomes a product of these actions for the different links you're building up. And you sort of, well, you can sort of figure out how to prune it from that because they're independent. I mean, because the logarithm of the action, the logarithm of probability, which is the action, is the sum of things. And if the best case for the other links plus the worst case for the one you're doing is below the threshold, then it's not going to affect things. That basically is how it works. I don't know. In a few words, that's how it is.
Okay, perfect. Yeah, thank you very much.
Any other questions? So I had a very minor question. Is it possible, or would it be useful to consider like this Thouless form of magnetic order, like a Thouless term tacked on to say a Kitaev spin liquid Hamiltonian? Would it be useful to look at this interaction, or would it not really make sense?
Yeah, I don't know about that. Yeah, I've never thought about that. The Kitaev model was constructed to have certain properties.
Yes, but I was thinking,
so
like,
what would be the point of adding? Is that to you want to put in there, or?
It's like similar to how people add like a Heisenberg term onto the Kitaev term, or like some other more complicated like exchange term to give me some incommensurate order. Like if I add another term onto it, like call it the Thouless term, what kind of magnetic order would you get in the entire system then?
Yeah. Well, I think with these ring exchanges, yeah, you can definitely change the phase diagram as I showed. If, for example, if you have just 2 and 3 exchanges, you're more or less led to either ferromagnetic or antiferromagnetic Heisenberg model. But once you add the 4 spin exchanges, you can get this other broken symmetry phase. Yeah. So it's certainly true that you could change the phases by doing that. But I can't say more than that.
Okay. So I think if there aren't any more questions, let's thank Professor Ceperley again.
Okay. Okay. Thank you. Thanks for the questions.
Thank you, Professor. Great talk.